Okay, today we're going to be talking about 2-5, which is about infinite sets. So, one-to-one correspondence between two sets A and B is a rule or procedure that pairs each element of A with exactly one element in B, and each element of B with exactly one element of A. So, if you get one-to-one correspondence, you can say that those are equivalent sets. So, this first one on the left shows a pair of one-to-one correspondence. Each element goes to exactly 1. Now here is an example of one that's not, because here I have B going to 2 and 3 going to 2 different. They have to go to exactly 1. So this next one says establish one-to-one correspondence, and it's our natural numbers and even natural numbers. So it's already done for us, but I'm going to walk you through it. So you just rewrite the natural numbers, and since it's just 1's the first term, 2's the second term, 3's the third term, 4's the fourth term, it's just n is the nth term because you're just repeating the numbers. Now for the even, it changes because it's 2, 4, 6, 8. So I'm taking the first term and I'm multiplying it by 2 because 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8. So it's 2n because you're taking the number of term and you're multiplying it by 2. So this shows 1-to-1 because each of these matches up with exactly 1. So when you go to write your rule, it would be n, double arrow to 2n, because it's every n element is matching up with 2n in the other set. So now it wants us to do that with the odd natural numbers. So I would rewrite my natural numbers. That's n. And then I need to match it up with my odd. So here, and I need to figure out what the rule is. Now, we have 1 as our first term, and then we have 3, 5, 7. So I can't say it stays in the number of terms, because if I was doing that, it'd be 1, 2, but instead it's 1, 3. So I need to figure out how I can go and make the second term a 3. Well, I could just take my n plus 1, but then when I get to 5, which would be my third term, 3 plus 1 is 4, not 5. So that doesn't work. So then I got to figure out another way. Well, to make this 3, I could, if I took the number of terms, multiply it by 2, that gets me 4. And then 4 minus 1 is 3. So then this is my third term. So 2 times 3 is 6, minus 1 is 5. So far it's working. 2 times 4 is 8, and 8 minus 1 is 7. And then the 2 times 1 would have been 2, minus 1 is 1. So this is taking the number of terms, multiplying it by 2, and then subtracting 1. So this shows one-to-one correspondence. So this would be our rule. So then over here, an infinite set, you can say something is an infinite set if you can show that it has one-to-one correspondence with a proper subset. So this first one just said prove the set of natural numbers n is a proper subset. Well, or is a infinite set. We did that in the first two examples here because both of these are showing one-to-one correspondence with a proper subset. So then they want us to do that with this set, which is 5, 10, 15, 20. So 5, 10, 15, 20. Now, 5 is the first one, 10 is the second. Well, to get from 1 to 5 and 2 to 10, you multiply by 5. So you're taking the term and multiplying it by 5. So that's 5n. Now, the easiest way to get a proper subset is to take this and multiply by 2, which gets me 10n. So that's the easiest way. So now instead of my first number being 5, I would take 10 times 1, which is 10. 10 times 2, 20. 10 times 3, 30, 10 times 4, 40. So this is what shows my one-to-one correspondence for here. So since I showed that it has one-to-one correspondence with its own subset, this is going to be an infinite set. So one type of infinite set, to find them, you'd find the cardinality. So before, we had finite cardinality, where we can just count the exact number of elements in there. So here, the cardinality of natural numbers is this nice little n0 symbol, which is alpha null. So it's the first transfinite number. It's also the smallest type of infinity because there are multiple types of infinity. So this little box here just says if there is a one-to-one correspondence between two sets A and B, then A and B have the same cardinality. So these sets that we showed were with our natural numbers, they have the same exact cardinality. So they would also be alpha null cardinalities. So on page 2, the first example here, the first two examples have us practicing that. So it wants us to take our natural numbers in integers. So first I'm going to have my natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. ... Now this time, because of how the integers are, how they're negative and positive numbers, we actually have to include both rules for our natural numbers. So the first ones are odds, which were 2n minus 1, and then it was evens, which would be 2n. So now we're writing our natural numbers in those two orders. So then I have to figure out how to match it up with integers. Now you'd want to start in the middle, which is 0, and then alternate negative, positive whole numbers. And then we have to figure out what the rules are for these ones. So we're going to try and match these up, match these up. So I'm trying to pair them up now so we can see how we want to match them up. So my first term is 0. So the one way I could think of doing this, so I'm just going to write this in a different color because it's just an idea, is I could take the term, which would be n, and subtract 1. So that does work for this one because it gets me 0. But it's alternating every other. So I would try it again here. Well, this is technically the second term, and this 2 minus 1 is 1. But I need a negative 1. So that idea doesn't necessarily work right at the beginning. So then let's try if I take the negative version of it and add 1, because negative 1 plus 1 is 0. So I try that here. Well, this is the second term, so negative 2 plus 1 gets me negative 1. So then I try it for this term. Well, that's the third term, so negative 3 plus 1 is negative 2. Try here, so negative 4 plus 1, negative 3. And I try here, which is the fifth term, gets me negative 4. So that would be my term here. So then I have to figure out what I put for all the other ones. So this is my first term for the second set, my second term, third term, fourth term. Well, those are just the regular numbers, so that would be n. So this time we have two rules. We have 2n minus 1 matches up with the negative n plus 1, and the 2n matches up with our n. So these are the rules that help us show that they have the same cardinality. So this next one, we have to show that m has the same cardinality as these. So we want to pass with n0. So we want to match it up with our natural numbers. So I'm going to go ahead and write my natural numbers. So 1, 2, 3, 4, 5. I'll go to 6. ... Our natural numbers are n for this one because there's going to be a nice set. So we have 1/2, 1/3, 1/4, 1/5. So this needs to match up here. This needs to match up with this one. This needs to match up here. Ooh, match up here. So I need 1/6 and 1/7. So those are just representing the number of terms this time. So then I got to figure out this. So all of them have 1 on top. So 1's going to stay the same for each of those when I come up with my new formula. Now, this is the first term, but my bottom's 2. So I could take n plus 1 because 1 plus 1 gets me 1/2. But then I have to see if that makes it true for the second one. So this would be 2, because it's the second term, plus 1 gets me 1/3. So that works. The third term gets me 1/4. Fourth term gets me 1/5. The fifth term gets me 1/6. And the sixth term gets me 1/7. So this actually did work. So my formula would be 1 over n plus 1. So this shows 1-to-1 correspondence, which shows that it is a finite set. So here that we have a theorem. The set Q plus, so it's positive rational numbers, is equivalent to the set n of natural numbers. So it's just saying that the number of elements in both of those are the same. And then it's using a little table to kind of show you that. So here, they're taking 1 and putting it over 1. And then all these have 1 on top. And then all the numbers going down are on the bottom. So these going across have 2, 3, 4. And it's showing that they continuously match up in a 1-to-1 correspondence throughout this whole table. So over here. So a set is a countable set if and only if it is a finite set or an infinite set that is equivalent to the natural numbers. So if it has an exact countable number or if it's the alpha null cardinality, then it's a countable set. So next, it said, are all infinite sets countable? Well, if it can't be a subset of our natural numbers, then no, it's not countable. So this theorem, the set A equals x such that x is a real number and it's between 0 and 1 is not a countable set because it's saying we're not going to be able to prove it. So they did a proof by contradiction, which just means you assume the opposite, and when you get to your proof, you actually contradicted yourself in the end. So this just kind of walks us through it. So it's saying, hey, here are natural numbers, A1, A2, A3, all the way there. And then the diagonal technique, so construct the numbers of D as follows. D differs from A1 in the first decimal. So it's just kind of walking these down, and we end up with a contradiction. So we're not going to have to worry about that too much. So on to the next thing, page. Oops. So it is said to be uncountable. The cardinality is denoted by C, which is a continuum. So continuum is bigger than alpha null. So it's just saying it's a bigger set of infinity. So this little table kind of helps you get a cheat sheet of what the cardinality of some infinite sets are. So our natural numbers, integers, and rational numbers are all going to be alpha null. Our irrational numbers, any intervals that we have, and real numbers are all going to be a continuum, so C. So here, the power set of a set denoted P of A is a set of all subsets of A. So find the power set of A for A, B, C. So you're listing just a set of all the subsets. So this, to figure out how many subsets there were, I take 2 to the third power because there are 3 elements. So I need to have 8 things listed. So the first one is the empty set. Then I could have just A, I could have just B, I could have just C, I could have A and B, I could have A and C, I could have B and C, and I could have all 3, so A, B, and C. So that's 1, 2, 3, 4, 5, 6, 7, 8. So this is just you listing all of the subsets inside of a set. So I listed all 8 of them. So before I said list all the subsets, and you did that on a quiz. Now you're listing them all, but you're putting braces on each side to represent the power set. So then the next one, oops, wrong thing. Cantor's theorem, so it says let S be any set, the power set of S has the cardinality that is larger than the cardinality of S. So it's just saying if you take the cardinality of your power set, it's going to have a bigger cardinality than the original set, which is shown here in this example because the cardinality of my set here was 3, but the cardinality of this set, there are 8 things in there. So it has a cardinality of 8. So it's just saying that this number should always be bigger than that one. And then it says that the power of the natural numbers between 0 and 1, x such that r, or x is an element of r such that it's between 0 and 1. So this is all it for the 2-5 notes.